Let me remind you what we have done on the last lecture. So we started to consider interpolation problem, and I gave you motivation. And so let me remind you. So essentially, you have data set Dn, which consists of pairs of numbers xi, yi. I goes from 1 to n. So what it means that on the xy plane, you have, pay attention, it's not necessary to have it in this particular order, but usually we order it, but it's not necessary. And for every x, you have corresponding points. So, and the problem of interpolation is to find the curve which goes through all these points, and essentially you decide what type of curve it will be. So, but first we gave also definition of linear independence of vectors. So the following, okay. The collection of vectors is linearly independent if and only if the following expression has only trivial solution. So just a reminder. So in other words, you cannot express one vector through linear combination of others. So which means you can't express. So if it would be possible, let us say that C1 is not equal to 0, then you could write something like that: V1 equals to minus C2 over C1 V2 minus and so on minus Cn over C1 Vn. So you would be able to express one of the vectors through a linear combination of others. That's it. So okay. Pay attention that here in this definition, by linear combination, you could mean not only just column vector, right? But if we recall linear algebra, so by vector we call just an element of a vector space. For example, vector space of polynomials, matrices, and so on. So, okay, second definition is linear independence for functions. A collection of continuous functions phi n defined on an interval I included into the set of real numbers is linearly independent. If the only solution Ci goes from 1 to n to the following linear combination. Is, so the only solution is C1 equals to C2, Cn equals to 0. So in other words, once again, if we require these to be equal to 0 on the interval I, and and the only solution, pay attention, it has to be true for every value of x. So every value of x on the whole interval. Then if the only solution is the set of these coefficients which are all equal to 0, then these functions are called linearly independent. So once again, so idea here is that this definition is not necessary, because, as I said before, so you can consider vector here in this definition as in general, as a vector in general, which means element of a vector space. Okay, so and now the last definition, definition of interpolant and basis. Pay attention, so all these, so you don't need to write it down, so because all this is already available in the lecture Interp 1. Okay, consider the data set dn I goes from 1 to n. Choose an interval I included in the set of real numbers such that xi belong to this interval for all I. So x1, x2, and so on, all of them belong to this interval. As a basis, for interpolation of the data set dn, let us choose a collection of n linearly independent functions. So I will call this Bn. Furthermore, suppose there exist constants C1, C2, and so on till Cn, such that C1 phi 1 xi plus C2 phi 2 xi plus and so on plus Cn phi n I equals to yi for all I 1, 2, and so on till n. Then we say that p of x, which is, okay, I will write it first in this form, and then in this form. So we will call this is an interpolant of the data set dn with respect to the basis bn. Okay, so it's not necessarily to assume continuity of these functions, but it's just simpler. And the examples which we will use, so for all of them, we will consider continuous, even more the regular functions. I mean, analytic functions. Okay. Now, the question is that if we have a look at this definition, we are saying, suppose there exist constants such that we can essentially say that our y's are can be represented as linear combination of our basis functions in the corresponding values of x. So once again, so idea is that we instead of having f of x such that f of xi equals to yi, so instead we are trying to find such linear combination of our basis functions which would coincide in points x1, x2, and xn with f of x. So essentially, we have, this is our f of x, right? So, but we don't know what this f of x is. We know only values of this function in the corresponding points. So as a result, we are just saying that, okay, let us suppose that, so we have some basis of functions, and let us try to represent our function, replace it with some linear combination of functions from the basis. Okay, such that it would coincide with values, corresponding values in the points, all the data points which we are given. So the fact is that, so have a look here, we are saying that suppose there exists such set of constants. So it's not yet clear whether this problem is well defined or not. Okay, let us formulate a theorem which will address this issue. For a positive integer n, let a data set dn and the basis bn be given, and assume xi not equals to xj for all I not equal to j. In other words, the points, so-called sample points, so where we have values of our unknown function, right? So all points are distinct. In addition, let us define the vectors vi by vi is phi I x1, phi I x2, phi I xn. So in other words, we have chosen one of the functions, right? So for example, phi I, so let's say v2 vector will be nothing else but phi 2 at the point x1, phi 2 at the point x2, and so on till phi 2 at the point xn. This is just an example for I equal to 2. Okay, if the collection I equal to 1 to n is linearly independent, then the interpolant f of the data set dn with respect to basis bn exists and is unique. Okay, so it essentially tells us that it's enough to have functions which are, okay, let us say continuous and what is more important, linearly independent. And then using these n functions, we can find interpolant, which means linear combination like that, which will go, and these resulting functions will go, oh, oops, nobody corrected me. So we'll go through all the points, all the data points, and we can use it as a result as a interpolant, right? So as a substitution for the function f, which we don't know. So proof is very simple. So we can introduce Vandermonde matrix. So pay attention, it depends only on the basis Bn and xi's positions of the point xi. So essentially this Vandermonde matrix, so you remember we introduced these vectors, column vectors vi's, right? So our Vandermonde matrix is nothing else but vector v1, then v2, and so on till vn. So pay attention. Every vector contains n entries, right? So it belongs to Rn, right? So as a result, we have here n vectors. So this is n by n matrix, right? Okay, so let me just write it. This is v1. This is v2. And so on. And this is Vn. So this is Vandermonde matrix. And then what is interesting that your interpolant, so what is the requirement? So what does it mean that we were able to find this interpolant pxi such that correspondingly C151 xi plus C252 xi so we require, what does it mean that our interpolant goes through all the data points? It means that at the point xi, this function has to be equal to corresponding yi. So it's essentially exactly this, that so this is y1, y2, y3, and so on, and this is yn, right? We require that instead of that, so we use some p of x, and this p of x has to go through all the points, corresponding points. So this is the requirement. But how can we write it? So let me just write it at the point x equal to 1. So we are getting y1 equals to c1 phi1 x1 plus c2 phi2 x1 right. At the point x2, it has to be equal to y2, right? So the same, pay attention, the same coefficient, right? The same functions, just the same linear combination of them. And so on. And at the point yn, at the point xn, it has to be equal to yn correspondingly. But then, if you will have a look, so how can you write it? You can write it as a vector of y's equal to, and here is exactly phi1 x1, phi1 x2, phi1 xn, phi2 x. So this one, right? x1, phi2 x2, and so on, phi2 xn. So these, right, form a corresponding column, and so on, till phi n, here it is, x1, x2, and this vector multiplied on the corresponding coefficient c1, c2, cn. So this is nothing else but Vandermonde matrix, right? So you could write it, let me call this vector coefficient c, this vector of right hand sides y, right? And then I'm getting v on c equals to y. So I'm getting system of linear equations. But by assumption, our functions phi1 and so on, right? Phi2 and so on, so they are linearly independent. Then what it means? It means that these coefficients, so pay attention, by assumption of the theorem, these column vectors, right, are linearly independent. So you see, if the collection of these vectors is linearly independent, so then it means that these column vectors are linearly independent, right? And if you remember linear algebra, so if we have linearly independent columns of a matrix, so then this matrix is non-singular. What it means that solution exists and unique. You can find it using something like that. Of course, you don't need to find the inverse Vandermonde matrix. So in many cases, so this is nothing else but system of linear equations, right? For the coefficients C1, C2, and so on till Cn, right? We have n by n matrix, right? And we know that solution exists and unique because this matrix is non-singular, because columns are linearly independent. So in other words, if you remember, in linear algebra, it's called the matrices of a full rank. So essentially, there will be, when you will be performing Gaussian elimination on it, there will be no free variables. Okay, so that's it. So we have proven that solution exists and unique. End of the proof. So essentially, it means that we can find an interpolation if we have, if we satisfy conditions of the theorem, right? We have distinct points, x1, x2, and so on till xn. We have a basis of functions, which means that functions are linearly independent and so on. Then we can form these vectors vi, right? So columns of the Vandermonde matrix, which are appearing just from here, right? So we are essentially trying to find such linear combinations, right? And we are forming this system of linear equations. So this is nothing else but system of linear equations. By definition, because columns are linearly independent, so solution exists and unique by the statement of the theorem, right? So because columns, we require that these columns are linearly independent. That's it. So it means that we can find the solution. So let us consider an example. Let us consider the following B4. So you can write it as xi. I goes from 0 to 3, or I can say that I equal to 0 gives you 1, x squared, x cubed, just like that. Okay, and let us consider the following set of points: 0, 1, 1, 4, 2, 1, 3, 1. So 4 points, pay attention, 4 vectors in the basis, right? 4 points. So now I'm trying to find my interpolant in the following form. So it's I goes from 0 to 3, ci x to the power I, or in other words, c0 multiplied by 1 plus c1 multiplied by x plus c2 multiplied by x squared plus c3 multiplied by x cubed. Essentially, could you tell me how the function of this type is called? Function which is linear combination of x in different powers. How it is called?
Polynomial?
Exactly, polynomial. So this is these 1x, x squared, x cubed, they form a basis, right? So called basis of monomials. So by monomial, we call the simplest polynomial of the given degree, right? So the simplest polynomial of degree 0 is just constant 1. The simplest polynomial of degree 1 is just x. The simplest polynomial of degree 2 is x squared. And the simplest polynomial of degree 3 is x cubed, right? So this is called basis of monomials. And so essentially, this is also so-called natural basis for the space vector space of polynomials of degree 3. So what we are trying to do, we are trying to find these coefficients C0, C1, C2, C3, right? For which will satisfy this set of data set. So pay attention that what will be these. So following. So what are the coefficients at the basis vectors in linear algebra, which give you the corresponding vector in your vector space? How they are called? Do you remember? Just let me remind you. So for example, we have 1, 2, 3 in 3-dimensional space. So natural basis for the 3-dimensional space is the following. So could you tell me what will be the coefficient here?
1.
Right. Here?
2.
Exactly. Here?
3.
3, right? So these are nothing else but so-called coordinates, right? In the basis, in this natural basis. So this is E1, this is E2, this is E3. So essentially what we are trying to do, we are trying to find coordinates in the basis of monomials of the function, which will satisfy all these 4 data points. How can we do this? So essentially, pay attention. We are trying to find these, and according to the our data set, P of 0 is equal to 1. So pay attention. Here, x is equal to 0, y is equal to 1, right? P of 1 is equal to 4, x equal to 1, y, corresponding y has to be, so is equal to 4. P of 2 is equal to 1, and P of 3 is equal to 1 again. Do you understand what I'm doing? Where I got these,
Yes.
these equalities? Any questions? Because it's extremely important. This is what you will be doing during all these, during your homework, for example. Okay, now let us write these using this expression. P at 0 equals to C0 plus C1 multiplied by 0 plus C2 multiplied by 0 plus C3 multiplied by 0, right? And this has to be equal to 1. P at 1, so now I'm using this equality, is C0 plus C1 multiplied by 1 plus C2 multiplied by 1 squared, right? Plus C3 multiplied by 1 cube equals to 4. P at 2. Could you please tell me what it will be equal to? So go ahead, don't be afraid.
C0 plus C1 times
X equal to 2, right? So you just substitute, instead of X, you substitute 2, right?
Correct.
Okay, let us go further.
C2 to square.
Which is equal to 4, right?
Yes. And C3 to cube.
Which is equal to 8, right? And it equals to what?
1.
1, right? Because we were doing this equality, right? Now, let us take into account the last equality, which will give us what? Could you tell me?
C0 plus C4 times 3 plus C2 times 3 squared, which is 9, plus C3 times 3 cubed, which is 27, equals 1.
Thank you. So we got 4 equations for 4 unknowns, right? So we don't know C0, C1, C2, C3. So, but we got 4 equations for these 4 unknowns. So we can write the following system of linear equations. One, could you tell me the first line? So C0, C1, C2, C3. So could you tell me what will be the first line in the matrix? Just coefficients here, right?
Would it be 1, 0, 0, 0?
Exactly. Second line.
1, 1, 1, 1.
So just these coefficients, right? Okay. The third line.
1, 2, 4, 8.
Right. Just corresponding these. Okay. And the fourth line. The fourth row.
1, 3, 9, 27.
Exactly. Thank you very much. So, and what will be the right-hand side? It's nothing else but this vector, right? 1, 4, 1, 1, right? So we got system of linear equations, right? So you already know how to solve this system of linear equations, right? Through LU factorization, or you can use in MATLAB this inverse. You can find inverse of this matrix, or you can just use this backslash, so operator. So okay, I will just give you the solution. So as a result, you can have a look at the lecture. So there is a plot 1, figure 1, which shows that really this function which we have found. So essentially, it's the following function: 1, okay, multiplied by 1, 9 multiplied by x, right? So this is my C0, C1, C2, C3, right? So minus 15 halves x squared plus 3 halves x cubed. So this function goes through all these data points. So if you have a look at the lecture, which is posted already, so there is a figure 1, so you can have a look there. So in general, this is a special case of so-called polynomial interpolation. So what is interesting, that if you have n points, so you can always use correspondingly the basis of monomials. And using this basis, so you can find polynomial interpolant. So this is essentially what we will be doing most of the time during studying interpolation. We will use polynomials to interpolate the function, well, the data set. So it's not the only way. So there is also trigonometric. So phi1 of x is 1, phi2 of x is sine of x, phi3 of x is cosine of x, phi4 of x is sine of 2x, phi of x is cosine of 2x, 6 of x is sine of 3x, 7 of x is cosine of 3x, and so on. So if you represent your function f of x as a c1 on 1 plus, you can say that this is cosine of 0 multiplied on x, right? Plus c2 sine x plus, sorry, allergies giving me troubles, c4 sine 2x, c5 cosine 2x, and so on. So do you know how such representation as a linear combination of sines and cosines is called? So just expansion of your function in the series of sines and cosines of x, 2x, 3x, 4x, or similar things. So on the interval, let us consider an interval from 0 to 2 pi. So then I know that my function, and let us consider, for example, periodic functions. Then I can use this basis, right? Basis of, so all these functions are periodic on the interval from 0 to 2 pi, and I can represent my function through the linear combination of sines and cosines. So do you know by any chance how such representation is called?
Does it have anything to do with the Fourier transform?
Exactly. Okay, really it's discrete Fourier transform, but idea is the same. So have a look. So this is also nothing else but interpolation of some given points using trigonometric functions. The only thing is that in order to solve it, you need to use at least n square operations for n points. But there is a so-called fast Fourier transform algorithm which allows you, instead of n square, use n log n operations, which is way faster. You can find different other bases, no problem. So this is why essentially, but we will not use it. So, and I will stop here on that. So okay, So I'm just explaining that you can use different bases to interpolate your function. So what we will be doing, we will be using polynomial interpolation. For polynomial interpolation, you can use different bases as well, but one of the easiest to start with is the basis of monomials. But as you will see on the next lecture, this is not the easiest basis to solve the problem, because you see you are getting, for example, here, right? You are getting dense matrix, so there are not so many zeros there, right? So if you would be considering not the point x equal to 0, right? So we would have practically no zeros in the matrix. And then you know that in general, to solve such a system, if you have a lot of points, what is the complexity? For n by n matrix, if n is large. So what is approximately complexity? How many floating point operations we need to perform to solve system like that?
This is approximately 2/3 n cubed.
Right, 2/3 n cubed approximately, right? For large n. Of course, you have an exact formula which you can use for small n, but it doesn't matter. No, it's not that important. But here we use n cube operations. As you will see later, you can just use different bases, and then you will be able to get this matrix not in the form of the dense matrix like here for the basis of monomials, but you will get it as the lower triangular one. For lower triangular matrix, how many operations do we need? Approximately.
Is it about n squared?
About n squared, right? So this is already this will be called Newton's method. So you see Newton worked here as well. So Newton was genius, really. So but this we will study on the next lecture. Now I wanted to give you a little bit more about linear systems. So I wanted to cover so-called iterative methods. So what they are? It's essentially, idea is the following. Before we were considering these LU factorization and so on, right? But LU factorization so gives you an answer, right? The problem is that in many cases you don't really need to have the full matrix, but in many cases also you need to find just an approximate solution. And for this approximate solution, it's too costly to spend these 2/3 of n cube operations just to get an approximate solution. So you don't need, in many cases, just to get exact solution. Approximate solution is good enough. And then you can do the following. So let us consider, for example, the following system of linear equations. So very simple system of linear equations. Okay, now, and let us consider initial guess. which is u naught is equal to 0 and v naught is equal to 0. Okay. Now, what we can do? Let us use the first equation to express u. And let us use the second equation to express v. Right? So you could say that, yeah, but the problem is that I don't know v and I don't know u, right? So, okay, no problem. So essentially you can formulate it as a fixed point iteration. Start from this initial condition and just perform iterations. Okay, let me stop sharing here and I will show you this from the book. Okay, so here it is. So you see, this is the problem. And I start from u naught, v naught, which are equal to 0, right? And just substitute them into this, into the right-hand side of these formulas. And you see, if I substitute here 0, 0, so this is what you get, right? And you're getting 5/3, 5/2. Okay, now I use this as my approximation. Again, substitute in these formulas here and here. Getting this, it gives me 5/6, 5/3. Now I use this as a current approximation, substitute into these formulas, right? Into these formulas. So substitute here, getting 10/9, 25/12. So exact solution is really, it's easy to find from here. It's 1, u equal to 1, v equal to 2. So you can see that here we are getting closer and closer to it. If we continue, what we can get just a better and better approximation. Clear? Is it clear or not? So what it is?
Yes.
Okay, now let me here it is. Now, let me consider exactly the same problem where I will just change order of the equations, right? I use u plus 2v equals to 5 and 3u plus v equals to 5. Okay, then from here I can express u as 5 minus 2v, right? And from here I can express v as 5 minus 3u, right? Looks like everything is simpler, right? And now let me just do exactly the same iterations as before. So, okay. Let me show you the result. So here it is. We start from exactly the same initial condition, initial guess. So, and when we substitute, we are getting after first iteration 5, then -5, -10, 25, 20. So you see we have divergence of the numerical method, right? So pay attention. I haven't changed the original equations. I just changed their order, right? So we know we know that exchange of the order should not. I mean, it doesn't affect the solution set. But for the fixed point iterations, you remember we had this condition for the convergence of the fixed point iterations. So for the fixed point iteration, unfortunately, these can be important already. So now let me introduce the definition. So in one case, you saw that we have convergence of the iterations to the solution. And in other case, we have divergent iterations. So let me introduce a definition here. The matrix is strictly diagonally dominant if for essentially if the magnitude of the diagonal element is strictly more than sum. So you see, j is not equal to I. So I is the row, right? So if the magnitude of the diagonal element is strictly more than sum of all other elements in the same row. Clear or not? So here, and if we come, so essentially, if we have a look here, so what is the coefficients matrix? 3, 1, 1, 2, right? Okay, let me just discuss a theorem. Here it is. This is the coefficients matrix for the first example when we haven't exchanged the rows. 3, 1, 1, 2. So you see the main diagonal element is strictly more than sum of all our other elements. Okay, here we have just one element, which is 1, right? Here we have the same. So magnitude of the element on the main diagonal is strictly more than sum of the magnitudes of other elements in the same row. And for such situation, we have this theorem, which says that if n by n matrix is strictly diagonally dominant, then A is first of all non-singular, which means that solution exists and unique of such a system of linear equations, right? And for every vector B, for every starting guess, so doesn't matter where you start from, the Jacobi method applied to this converges to the unique solution. So pay attention that when we exchange the equations, right, change their order, so we just change the rows in our coefficients matrix, right? So, and have a look here, this matrix is already not diagonally dominant, right? Because magnitude of the main diagonal element is not strictly more than sum of the magnitudes of these elements. So we have larger elements here. Clear or not what I'm talking about?
It's clear.
So, yeah, I think it's clear. But if with this restriction on the fixed points, does that mean it's more difficult for the fixed point iteration to converge for larger matrices?
You see what is important here. So we essentially, this theorem gives you sufficient condition, right? So if matrix is strictly diagonally dominant, then it's non-singular. You see, then it's non-singular, and Jacobi method will converge to the unique solution from any case. So it's sufficient condition. So essentially, of course, a problem can be solved by using different methods and so on, right? So it's just if it's strictly diagonally dominant, then Jacobi method converges, right? So and then, so you see, it's just the fixed point iterations for this particular method, Jacobi method. So yeah. So for example, for this matrix, you can see, so if I ask you to figure out whether they are diagonally dominant, so you see 3, magnitude of 3, strictly more than magnitude of 1 plus magnitude of -1, right? So then magnitude of 5, -5, right, is strictly more than magnitude of 2 plus magnitude of 2, and so on. So here, 8, magnitude of 8, strictly more than 6 plus 1, right? Here it is. And here, it will not work. For the last row, for example, right? Magnitude of 3, magnitude of 2 will be, you cannot say that it's strictly more than magnitude of 9 plus magnitude of 2, right? Okay. So really, you can formulate the Jacobi method for larger metrics in the following form. So you can say that your A can be represented as lower entries, diagonal entries, and upper entries in the matrix. So just, okay, let me probably stop sharing here and share here. So essentially, your matrix A can be represented as your diagonal elements, right? Then this is U part of the matrix, and these are L part of the matrix. So you can say that this is essentially L plus D, which is just diagonal matrix, plus U, right? So you can split this matrix into these parts. And then your AX equals to B system of linear equations can be represented as L plus D plus U X equals to B. And then essentially, when you can reformulate the Jacobi in the following form. And it's very easy to invert the diagonal matrix, so just inverse elements on the diagonal, so you're getting so you could say that you use the following iteration process. Okay, so so these you can consider as a Jacobi method for the arbitrary matrix. Okay, I will finish. We'll go through the Gauss-Seidel method and successive over relaxation in on the next lecture.